All right. Welcome everyone to our SkAI Colloquium. So if you are first timer here, welcome. We have two QR codes you can scan and find out more information about the space and the SkAI Center in general. And if you have questions, I'm going to direct you to Alex here in front. All right. Okay. So I have a few announcements. One is some of our Friday, there's some change to our Friday schedule. We're moving the talks to 2:30 p.m., so slightly earlier starting this week. And it'll be mostly chalk talks, but there will be a few works in progress updates there. So watch out for the emails and you'll hear more about them. And then next week, we have our works in progress on Wednesday by Alex and Aravinda. It'll be here and over on Zoom as usual. Make sure you RSVP. Thank you. So what else? So on the same day, we also have an early career scientist game night mixer at 4 to 6. Sounds very exciting. Uh, no registration required, but if you don't have access to the building yet, please request for a pass so you can come upstairs. Otherwise, we're going to have a lobby session of the game night, right? You don't want that. Okay. Yeah. And then we also have I guess, an event at Urbana Champaign called Let's Talk About AI, also on the same day. And here's a QR code you can scan and find out more about it. Then there's an AI hackathon happening. Where's Gotham?
Gotham is probably on his way.
Okay.
Or he may be at the conference.
I think I saw him outside, but anyways. So yeah. So we have Rubin Alerts and AI Hackathon happening on April 1st through 3rd. They're going to be here. There's is a hybrid option available. And then we have, nice lodging rates and the rest of the information here. So if you're interested, the registration deadline is coming up. Make sure you register by then. And then there's a QR code for that. All right. So I'll leave it up for people to take a picture. All right.
March 20th is not Monday, right?
Mm,
Monday the 22nd or something.
okay. So is the
Third, yeah.
is the deadline March 20th or next Monday?
It should be March 20th.
Okay.
Maybe just the Monday is wrong. And also Gotham is just going to walk into the room.
Okay. So we can wait.
Did he leave? I just saw him.
Oh, he heard us.
Okay, maybe not. If he escaped.
All right. If he swings by, we can ask him to clarify on that the registration deadline. But okay. All right. So, we have two exciting events coming up soon. So mark your calendar. We have a SkAI Sprint on May 28th. And we are trying to bring together the research software engineers for a full day, focus on co-working. So that'll be a hopefully very productive day. And then the next day, May 29th, we have our SkAI Fest happening. So it is an internal workshop for all SkAI members. There'll be panel discussion, lightning talk, poster sessions to highlight all of the research happening at SkAI. Okay, so watch out for your email for more announcements and do sign up for these events. Okay. All right, so that brings me to the end of announcement, and we're going to switch over for the colloquium. So today we're very happy to have Yuanyuan Shi, assistant professor from University of California, San Diego. She is with the Department of Electrical and Computer Engineering, also affiliated with their UCSD Center for Energy Research and Machine Intelligence Computing Security Center. She received her PhD from University of Washington, followed by a postdoc at Caltech. So she was initially scheduled to be here in person, unfortunately had some health issues, and now she's only joining us over Zoom. But if you have questions, like you would like to have further discussion after the talk, feel free to email her and schedule. afterwards. Okay. All right, Yuanyuan, are you ready? I think
Oh,
we're gonna
yes, sure.
switch over to you. Oh, and also because the speaker is virtual, when you want to engage with her, wait until you get the mic and then say your name before we start the discussion here. Okay.
Yes.
Yeah, thanks so much, Ermin, for the kind introduction and the invitation. Yeah, hi everyone. I'm Yuanyuan. I'm sorry that due to some health issues, I cannot travel and give the talk in person. But this is my email, and I'm happy to. If you have any questions or if you like to schedule any follow-up discussions, feel free to reach out to me. So today I will share some of our work on neural operator learning for control. Right, so I hope some of the topics, I know this is a astrophysics and plus AI seminar, so I hope some of the AI content of this talk could find connections to your research, and we could have a like discussion over it. To start with, I want to first acknowledge all the students and colleagues in collaboration for this work. So Luke is currently a fourth-year PhD student. He's a main leader and driver for all the series of work we have. And this work we're in collaboration with Professor Miroslav Kristic and Professor Nikolai Atesnov and UCSD together with their students, Pezia and Shiraz. So this is the outline for today's talk. I will first give some motivation and try to motivate like the different operators arise in control problems, and also give some background on what is neural operator learning if you haven't got a chance to know about this set of methods. And then I will kind of cover two case studies we did exploring neural operator learning for control problems, including both delay problems in ODEs and the control of partial differential equation system. In the end, I want to highlight some opportunities and challenges that we were thinking on neural operator learning and control problems. I think we're going to skip this part 4. Okay, so I want to first start by motivating what are the operators and what is operator learning. We can consider this very simple linear system. X dot equals AX plus BU, and then you're given the initial condition. Right, and the solution of this linear system actually have this explicit form, right? So any time step capital T, so the solution of this ODE is given by this closed form. And then you can view there is a mapping, right? If you change this initial condition x0, or you have chosen a different sequence of control input u of t, right? So these are all going to change your solution and this capital T. So we can define this operator from a vector and a function to another vector, right? As a solution operator for this ODE. And for this linear system, so we're lucky, so we can actually write out this operator explicitly. However, for most general nonlinear ODEs, there are no such explicit solution operator available. So that means if you change the initial condition or you change a sequence of input, right, you need to call some perhaps expensive solvers, right, to resolve this. And you can imagine if you have a black box article, right, that can, if you give any initial condition, any control sequence, that can just direct to predict you the solution of this ODE, that will be very desirable, especially for real-time applications. So I want to give another motivation that are solving PDEs, right? Solving PDEs are arise in various of science and engineering problems. So if you consider this following PDE problem, right, kxx minus kyy equal to some right-hand side terms defined in a triangular domain. So with a different lambda y that may corresponding to a different Planck coefficient, right? So you need to resolve this PDE. And then we can define also the solution of this PDE as an operator learning problem. So given a new system, right, of lambda y, which is a function, right, is a function of y. And then if you want to just predict the PDE solution, it's kxy, so it's a function of two variables. So actually, if you can solve this about PDE for any arbitrary given lambda y, that will actually give you this control kernel for a class of PDE control problems, that is a reaction diffusion problems. And there are many other PDEs that you may want to solve, right, for your different scientific and engineering problems. So why do we ever want to learn or approximate these operators? Because rather than solving those equations using numerical solvers, the machine learning surrogate models, if it can approximate those operators accurately, it can significantly reduce the computing time from the orders of tens to thousands or even larger, depends on the complexity of the problem. And what we're going to show you is in our work, because we mainly consider operator learning in control problems. So what we can achieve is not only acceleration, but we can maintain the guarantees as a control engineer and scientists care about. But maybe in your problems, you have different kind of guarantees. So when you think about this type of operator learning problems, right, you can develop new sort of guarantees that matters for your own application problems, besides leveraging the acceleration. So what we're going to show in the talk is we're going to show those operator learning enables control of ODE systems with long delays, where we're essentially approximating ODE solutions and repeatedly using it. And we're also going to show you this operator learning can be very useful in PDE controls. This part we may not get a chance to talk about, but this is in a motion planning setting for robots. If you have many obstacles, you want to go from one place to the other place, you want to navigate, that actually also entails solving some sort of PDE. It's a Hamilton-Jacobian type of PDE, and when you use neural operators, it can also significantly accelerate it while preserving the guarantees. Okay, so then I want to kind of give a quick intro about what is neural operators. We all know about what is a neural network, right? So a neural network essentially is try to approximate some vector-to-vector function mappings. For example, if you have an input vector x and you have an output vector y, there are various of different neural network architectures, but the most simple one could be the multi-layer perceptual model, where you take the input vector, then you do some matrix multiplication, going through the nonlinear activation functions, could be ReLU, could be sigmoid, and if you go through many layers of those, then you predict the output y. So both the input and output to the neural network models, they are vectors. And neural operators are in recent years, a new framework that tried to generalize the standard neural network learning to approximate mappings in the infinite dimensional function space. So you can imagine the input to a neural operator is a function, and the output of a neural operator is also a function. So we're essentially trying to approximate this operator map between the input function u of x to output function v of y. And there are a lot of different kind of neural operator architectures. I'm going to show you some in the next two slides. But a recent work from Caltech unified all these different neural operators, right, into this uniform framework. So where you can imagine is a neural operator usually consists of three components, because we're trying to learn this operator mapping between the input function space V, right, to the output U to the output function space V, right? So you will first, in general, have a projection layer that projects this infinite dimensional function space to some finite dimensional space. And then you're going to learn the approximation in this finite dimensional space. And then you will have another module that projects back of those finite dimension approximation, again, back to the output function space, this infinite dimension space. And then while you do this, where this combination of the three parts will preserve some important guarantees, which is this universal approximation theorem. So this is saying, right, if your input function are continuous functions and your output function is also a set of continuous functions. And then if your input function space is compact, and then this operator you try to approximate is continuous. So under those conditions, actually you can show for any operator mappings, right, that you're trying to approximate, and for any desired accuracy you want to achieve, like this epsilon you want to achieve, no matter it's 0.1 or 0.001, right? So there always exists a neural operator that is g of hat that can approximate this ground truth operator, right, within your desired accuracy for all possible functions and for all possible points you want to query the function and the output function space. So this is what empowers a lot for our control applications, because essentially we're going to quantify, right, in a control system, what is a desired learning accuracy. And then we're going to show whether we can always establish a neural operator that can approximate those true operators within those desired accuracy. Right, but that is a theory behind a neural operator. So as where neural networks is empowered by universal approximation of approximating functions, these neural operators now are endured with the capacity of approximating any continuous operators between the infinite dimensional function space. So here are some popular neural operator architectures. So I listed two, but there are actually many more if you look into it. So those are kind of one of the earliest neural operator architectures. On the left, what you have is a deep operator network, or called a deep O-net. So the main idea is if you have an input function u of x, right, and then you have a bunch of sensors, right, in the input domain, then you're going to sample and evaluate this input function, right, and this maybe endpoint. And then those evaluate points, right, is a finite dimensional approximation of this infinite dimension function space, right? But they're not necessarily be the best basis, right, for reconstructing the output function. So those sampled inputs will be encoded by a branch network, and then that will become like a basis, right, for how you're going to interpret the output function, right? And then depends on where you want to query the output function at, right? So you go through another neural network that gives you the coefficient, right, for combining those bases. So that is how you get the output function evaluation and any arbitrary point y. And you can view deep O-net as a neural network constructed a finite dimensional basis for the infinite dimensional function space, but then those spaces depends on where you want to query the output function at, right? So they're query point dependent basis, not like a fixed set of basis. And then there are another very popular neural operator architecture that calls Fourier neural operator, or FNO. So instead of using neural network as a functional basis, they're essentially using the popular Fourier basis. So if we have the input function u of x, so what we're going to do is we first going to do Fourier we first lift it out to do a lifting, right, using the projection matrix, and then we're going to do Fourier transform, and then we learn in the Fourier domain, right, in the frequency domain, and then we do inverse Fourier transform to convert back to the regular spatial and temporal domain. So essentially, we're using the Fourier basis for learning this function-to-function operator mappings. And actually, there are more architectures in the recent years, like including using transformer to find those bases, and also like Laplace neural operator and many more beyond that. But the interesting idea is behind this, the unifying paper I mentioned early, is as long as you can put your different neural operator design in this uniform representation, right? The projection, the finite dimension approximation, and then the projection back. So you can preserve this nice universal approximation guarantees, regardless of your architectural choice. So I hope I have convinced you there are different types of operator learning problems arise in solving ODEs, PDEs, and in different type of scientific problems. And then where we required and where we empowered by neural operator is acceleration and the approximation, rigorous approximation guarantees, given the conditions are satisfied. And you have a full set of tools, right, that different neural operator designs that you can choose for your problems. So next, I want to show you kind of two case studies that we have developed and for control applications. Maybe if there are any questions, or should I continue? If I didn't see any questions, maybe I can keep going and I can answer all the questions in the end. Okay, so I'm going to start from a delay control problems. So delay systems, there are a lot of delay problems, right? In the real world, the delays could come from sensing and computation or communication. For example, you have this autonomous vehicles running on the road, right? They have cameras, and then they gather the sensing data and then maybe go through some large model, right? Large vision language action models, right? The processing may take a few hundred milliseconds, but by the time that you output your action, the scenarios, like the trajectories of other vehicles or pedestrians or the car itself, may already change, right? So you may want to compensate for this delay to account for the current situation. Or in teleoperation, right? It could be surgical or even teleoperation for some space exploration tasks, right? So the delays could significantly impact the system efficiency. And also in a lot of cyber-physical systems like power grid, if you have communication, neighbors, transport information, right, like delays can also critically impact the system performance or even lead to instability. So mathematically, we can formulate this nonlinear system under delays in this general form. So X is your state and F is the dynamics. So your state evolution depends on the current state and some delayed input, U of t minus d, right? And then in general, as a control engineer, we're going to design the controller, right? Try to stabilize or optimize some cost for these delay systems. However, because of any kind of delay that may arise in sensing, computation and communication. So by the time that this control input arrive in the system state already changed. So how can we account for these delays and maintain desirable system performance? So the idea is actually very intuitive. So why not we have a predictor? So because this control input will take d unit of time, right, to arrive at the system. So instead of using the current system state to determine our input to the system, so what we can do is we can predict, right, how the system state will evolve, right, d unit ahead. So instead of using this current state, if we can predict how the system state will evolve, right, for the d unit of time ahead of time, and then we can use this predicted state, which we denote as p of t here, right, and in part of our control, so that we can compensate for the delay. So this is what it's called the predictor feedback, and is one of the most popular method in handling various of delays in real world control systems. And now if we look at this predictor, so this predictor is essentially try to solve implicit ODE. Why I'm saying that? Because you can see this PT shows up in both the left-hand side and the right-hand side, right, of the equation. Because the P of t is given the current state is xt, and then account for this d unit time of delay, right? So this is my prediction for the future, right? So this is in this current form is a integral equation, but then if you take the time derivative on both sides, you can also get implicit ODE, right? So in order to solve for P of t, unless you have a linear system, your f is a linear, otherwise you usually don't have an explicit solution. So we will need some numerical approximation method. And it's more complicated than solving a standard ODE, because if you need some iterative solvers, like successive approximation, to solve this type of implicit equations, right? So if your dynamics is high dimension or stiff, so it's going to be computationally costly, and more important because we actually need this prediction in every time step when we want to do control, right? So for this current time step, we need to predict where d unit ahead of time the state will be, right? And then insert the control. And then after 1 second, right? And then we repredict. So this operator needs to be repeatedly evaluated online. So that is our main motivation. So why not we formulate this as an operator learning problem and try to approximate this implicit integral equation solutions, right? And then once we obtain a good approximation, we can repeatedly using this approximation online for predictor feedback control in delay systems. So with this approach, we need to train a neural operator once offline. And then in the feedback loop, we're going to repeatedly using it, capitalize the first inference time of deep learning. And this is how we define the predictor operator. So the predictor operator, the calligraphic P takes 2 inputs. So xt is a vector. So this is a current system state. And then ut is a function, right? So that's essentially is a function that maps the control input from t minus d to capital to t. So this is essentially the system control signal, right? For this d unit of time. So the output of this operator gives you the solution to of p t of capital PT. Okay, so now you may recall that we can formulate this as an operator learning problem, but then the first important question come to your mind is what properties, like can we approximate this map, right? Can we approximate this map to any desired accuracy that we would want? So we can actually answer this question firmly. Recall that in order for us being able to approximate an operator, right, where we need to show is this input function set needs to be compact, and this operator that we're approximating needs to be continuous. And actually in this delay predictor feedback case, the operator we're trying to approximate is essentially the solution operator of an ODE. So what we can show is if this dynamics is continuous, actually we can show this operator we're trying to approximate is also continuous. And it has actually a stronger notion of continuity is Lipschitz continuous, with the Lipschitz constant depends on your delay time d and also the Lipschitz of your dynamics, which is C of f. So the larger the delay is and the larger the system Lipschitz constant, that means how quickly your dynamics change. Later on, you will see it requires a tighter approximation of this operator to maintain stability of the system. So that is good news. So the operator is continuous. And as long as we restrict the training set in a compact set, right, then we can reassure ourselves this neural operator can approximate this desired, this true operator to any desired accuracy we want. And this is this is where essentially the theorem 1 set, right? So for any user's specified approximation accuracy epsilon, right, we can always train a neural operator that is calligraphic p hat, and that can approximate this original ODE solution, right, to this desired user-defined accuracy. So now the next question is, once you approximate this ODE solutions, right, and then you plug in this prediction, which is p hat of t, the future state prediction, into your closed loop predictor, right, feedback, which is plugged into the controller. Will the closed loop system still be stabilizing? And the good news is the stability guarantee will still be maintained. And what you essentially will do is you will have this set of input function, right, x and u of t. So that is your training set, right? So when you train your neural operator, you specify these regions. And inside these regions, you find your neural operators could achieve the maximum of training error epsilon star. Let's see. And then where we can show is then in the testing stage, right? So as long as your initial system state, right, is inside this region, which is this omega star, and then your closed loop system will always maintain the stability guarantee. So here, this beta is a class KL function. That means as t grows, right, then this term actually converge to 0. And then it will not exactly converge to the exact equilibrium, but it will converge to epsilon bar around the equilibrium. And this epsilon is basically your learning error of the neural operator. So where we obtain here is a semi-global type of guarantee. So if you want your neural operator can works for a large region of systems, what you can do is in your original training set, right, you just need to collect a diverse set of input functions and see different states, right? So the larger your training set is, then the larger you can enlarge this region that you can stabilize the system in the test case. And then the final system is stabilizing to this epsilon bar around the equilibrium, and how small this region will depends on how well your approximation error is. So to validate our results, we train actually a series of neural operators on a predictor for a manipulator, for robot manipulator task to tracking a sinusoid curve under delays. So here the delay is 0.5 seconds and without any compensation. So where you can observe is this manipulator is always shaking and fails to track the trajectory. And here this blue curve, the solid curve, is a desired trajectory you want to track. And then this green dotted curve is a successive approximation. It's essentially those numerical solver that you solve those integral equation to obtain your prediction. And then this orange curve is where we achieved under the neural operator approximation. Essentially here we use a Fourier neural operator, and you can see this is how tightly you predict the state. And despite some prediction errors, right, the closed loop system is always able to track this desired trajectory within this epsilon bar and the system remains stable. And what you can achieve using those neural operator approximation compared to the numerical solver is you could achieve over 100 times speed up. That means if your original control frequency is limited to 1 second, but here when using the neural operators, you can control at a much faster frequency, right, to achieve more high accuracy tracking performance, like you can do here like 100 hertz versus 1 hertz control for some more agile tasks. So in summary, so in this first part, we present a framework for real-time deployment of a predictor feedback for delay compensating that achieves hundreds of times speed up while can still maintain the rigorous stability guarantees. And what we achieve through the theory is we can show, we can relate the learning performance to the closed loop control performance. So the region of attraction of the controller is proportional to the size of your training data, and also your regulation bias, that is how close you can regulate the system to, is inverse proportional to the training set, and is proportional to your learning accuracy. And this paper was originally published in Alpha DC last year, which was received the Best Paper Finalist Award, and now is under review and tech. And since then, we have explored many extensions of this neural operator learning for delay problems, for where you have the delay, but it's not a constant delay D, but a time varying delay. And if D is unknown, so we are online approximating this D while also approximating the OD solutions. And when you have multiple input, that is particularly relevant to network systems, like if you have different sensors across a network, each one may have different delays, right? And you're having, you need to kind of approximate a nested of neural operators to compensate for this multi-input delays. So we have several extensions to make this more relevant to real-world problems. So given that, I want to also have some time in talking about the second case study we have done for control of PDE systems. So PDE systems also are very relevant in different science and engineering applications. So one application we have been working together with Los Alamos National Lab here is in controlling of particle accelerators. Essentially, you have the electric field, magnetic field, and beam dynamics, and you want to regulate the electric magnetic field so that your beam are shaped and accelerate to some desired accuracy, where we're currently developing some neural operator surrogate models for accelerating the simulation and for control of those systems. And another type of applications we have worked on is building control, like cooling and air quality control. They're essentially governed by fluid dynamics, right? And then further driven the Navier-Stokes equation, and then further driven by those velocity fields. You have the convection diffusion equation that governing the thermal and air quality constraints. And we have some ongoing work that are experimenting with buildings in anti-UCSD so that we can reduce the energy consumption but maintain the indoor air quality. For example, you can imagine some people may get sick, and you want to regulate the air quality so that to reduce infection risk, right? And actually, a lot of traffic problems, like if you want to model the macro scale traffic, it can also be used PDEs. And I think in like astrophysics application, there are also popular PDE models of modeling different dynamics of interest. So a major challenge of arising in these PDE systems is often the computational complexity of solving repeatedly evaluating the solution, right? Of the PDEs. And also for controls, a further challenge is usually you only have very limited boundary actuation. You cannot control every single point within the spatial temporal domain, but you are only actuating at the boundary, and also you are only measuring the state and to some limited locations rather than getting the whole spatial temporal measurement. Given the time, I just want to show you one simple case study that we have explored on neural operator learning for control PDE systems, but I'd be happy to chat more about our other works if there are questions or time in the end. So if we consider this very simple 1D hyperbolic PDE with a boundary recirculation, right? So when this beta x is positive, and if you control and the right boundary, right, U of t is your control, and your control and the right-hand side boundary, which is this red line. So without any control, this system is actually unstable. It blows up. And this simple 1D PDE actually is a nice model to model the stop and go traffic behavior. So if you watch this famous experiment, you can see if there's some lead cars, right? If there's some cars in the beginning that drives irrationally, it hits the brakes, right? Some irregular, and then you're going to see this stop and go behavior will propagate, right, around the circle or along the highway. So at the end, you will see higher and higher oscillations, right? And then the system goes to unstable, right? And then the main idea for where we want to achieve in this PDE control task is simply stabilization, right? So without control, right, you can see the system goes to unstable. And our goal of control here is we want to, with only this boundary actuation, right, and the right-hand side boundary, U1 of t, right, we want to stabilize the system, right, despite the initial state, right, is initial condition is have disturbance, but we, with our boundary control, we want to stabilize. And the main idea for this controller we designed is called, it's based on the backstepping idea. So this is the original system. And the main idea of backstepping transformation, backstepping control, is we want to find a transformation that we can transform this original unstable system to this right-hand system, right? It's a stable target system, right? Using two things. Using one is our control, boundary control. Second is a transformation that I will show you next. So this is original system, and this is a target system we want to achieve with the boundary control. Okay. And this system is equivalent under the transformation and the boundary control. And this is a backstepping kernel that can help you achieve this task. Essentially, you can relate your original system and the target system through this Volterra transformation, right? And this K is a control kernel essentially you want to design. So if you have this transformation, this is also gives you the boundary controller. So it's essentially a convolution of your control kernel with the measurement across the state. And so you can see this Kx here need to satisfy this integral equation. And for different plants, for different beta of x, you will have a different integral equation. So in order to control the system, you need to solve a different integral equation to solve your control kernels. What you can do here is we can leverage neural operator to approximate this integral equations inside the PDE control loop. And what I want to mention here is, although for this 1D hyperbolic PDE, this kernel is an integral equation. Actually, for all other type of PDE control problems, we worked on like parabolic PDEs or other types. So this kernel are always a PDE rather than an integral equation. So this will further motivate why you want to approximate this design using an operator. So essentially, those neural operators will take whatever system coefficient you have and try to give you the kernel design, right? And then what you can do in closed loop is you will use this operator given a new system, right? You will use this operator, right, to design the control kernel, and that will always give you the boundary control input that you can inject to the system. And maybe you already have an idea. So we essentially ask two questions. The first question is, can we learn a neural operator K that can approximate this kernel design PDE calligraphic K, right, to any user desired accuracy? And what do we require? So the requirement is for the universal approximation theorem, we need the input function set to be compact, and also we need to show this kernel we are approximating, right, our continuous operator. And recall that this is an operator we try to approximate that maps the system coefficient beta of x to this control kernel k of x. And or in convolution notion, this is a operator we try to approximate. So in order for the universal approximation theorem to hold, we need to show this operator is continuous, and we can actually show it is Lipschitz continuous with the Lipschitz constant depends on the L infinity norm of the coefficient of the plant. And therefore, as long as you limit your training data, right, training system in a compact set, we have already shown this operator to be approximate as continuous. So you can approximate this operator within this any user-defined accuracy epsilon. And then the next question, maybe you're already familiar. So here I show you one simulation result. Essentially, this is a plant, and this is our approximate kernel function. So both are functional mappings. And then this is the arrow between the true control kernel and our neural operator approximate kernel. So the next important question, maybe you already guessed it, so is once we plug in this approximation in closed loop, right? So are the closed loop systems stable? Right, so this is where we do. So for the, when you use the true kernel, right? So you will convert the original system into the target system, right? Which is stable. But now with this learning arrow, where we arrive is actually this perturb the target system. And this perturbation term, right, this delta x actually will depends on your approximation arrow. So this is a true operator, this is your neural operator approximation. So this term is epsilon bounded, right? So where we show here is this learning arrow now acting as a disturbance term, right, to the target system. And that gives us the following analysis, the Lyapunov analysis. So for any systems, right, as long as your learning arrow, your neural operator learning arrow is less than this epsilon star, like when you plug in this neural operator approximate control gain in the closed loop, we can show the closed loop PDE system can still be stabilized. And in this case, this is a better result, stronger result than what we achieve in the delay system, because it's actually exponential stability and to the equilibrium. And where you can see here, this epsilon, right, depends on a few things. So the larger the beta is, that means the more unstable your original system is, and then the smaller your approximation arrow needs to be. Right? So that means the more unstable the system, the tighter the neural approximation arrow needs to be. We think this is a pretty neat result because it's nicely connect your learning requirement and your control system properties. So for simple systems, right, you could have a coarse approximation, but for systems that is more unstable, right, without control, you actually need a tighter approximation yet to achieve stabilization. And here we have some numerics, right? So this is a open loop transport PDE without control. It's unstable. For both cases, the left-hand side is one system, the other side is another transport PDE with different destabilizing effect. And this is where we achieved with a neural operator-based PDE control. It can always stabilize the system. And compared to where you use a ground truth approximation, this is how far you are like in the transient, right, away from your nominal control. And then depends on the spatial discretization you go with, we can achieve a speed up from like tenths of order to thousands of orders. And this acceleration will be even amplified if you're dealing with a 2D or 3D systems, because here we're only controlling this 1D canonical PDE systems here. Okay, So as a summary, in the second part, we present a framework for neural operator-based PDE control. In particular, we explore this PDE control of a 1D transport PDE. We introduce a neural operator gain approximation to approximate this mapping from the system coefficient to the control gains. And we show within certain desired learning accuracy, you can maintain the rigorous closed loop stability guarantees. And speed up in producing these PD solutions is in the order of thousands threshold. And this paper was originally published in Transactions on Automatic Control. And since then, we have many extensions to parabolic PDEs and to, instead of learning the game, but to directly learning the control law, or for inverse problem that's based on limited measurement, how do you infer the complete state? And for adaptive control settings where you don't know the coefficient, so where you're estimating the system coefficient while doing control. And actually, we have designed this tool called PDE Control Gem, where we have incorporates this different canonical hyperbolic, parabolic, building control, and a few other traffic control examples inside it for benchmarking both model-based and data-driven boundary control problems. So we have this open sourced. So if you're interested, please check it out and let me know if you have any questions on this. So with this, I think I will skip this motion planning part given the time, and then just conclude with some challenge and opportunities we have seen on these lines of work. So in today's talk, I have shared some of our explorations and journeys on neural operator approximation of different nonlinear operator maps in control applications. So we're approximating those function-to-function operator mappings, not just approximating functions, right? And then we can show after the operator training, right? So the solutions of ODEs and PDEs are compressed to tens of microseconds, and which achieves significant acceleration compared to numerical solvers. And guarantees can be preserved, like stability in control, suboptimality in motion planning, which I did not have time to cover. And so under those neural operator approximations. So here are where I see some opportunities and challenge for further we develop these techniques on both control applications and beyond. So one thing is the data reliance. So the current way we're doing operator learning, or most people are doing neural operator learning, is still in the supervised learning regime. So that means we essentially need to collect a lot of training data. For example, in order to build the surrogate PDE solver, we first need to solve this PDE 1,000 times in building this large training data given different initial conditions, boundary conditions, right? And then you do supervised learning on top of it. But sometimes, like the application we're interested in developing surrogate model, they're like very expensive to gather this data, or even not possible to kind of sometimes computational prohibitive, right, to get this large amount of data, right? So how can we reduce the reliance on this label supervision, right, and use more of a unsupervised scheme with where I see very promising to push this to harder problems. And also beyond acceleration. So far where we have explored mostly on this operator learning for control, we're on accelerating, right? So where we already have the designs and of both the predictor feedback or the PDE controller. And operator learning is play a role there in accelerating, but it's not like discovering like new control laws or but where we can see is like actually AI could help discover many things, right? Generate music, image, document. So how about in control setting, can it help with discovery new control laws and state estimations, right, for PDE systems, where actually there are many systems that without stabilizing controller even discovered there. So I see there is a huge potential there. And also the functional encoding. So what I have shown you before, for both the DeepONet and the FNO, they actually have the a discretization invariance, right? You see, you can query the output function and any arbitrary point inside this continuous domain. However, for the input function encoding, it's still somewhat limited because you need to sample those function input, right, and embed it as this discretized representation. It's not like a truly functional embedding. So I think learning-wise, this is a good opportunity to further explore the functional encoding inside neural operator architectures. And last but not least, when we learning these mappings and then when we plug into the real system sometimes have a different dynamics than where we train the system on. And as time evolve, right, the system dynamics is also involved. That introduce all this interesting distributional shift and sim to real challenges, which is kind of one of the main challenge for maintain the good performance over time. So with all of this, I'd like to conclude my talk, and I'm happy to take any questions. Thanks so much for your attention.
Questions, comments? Also, if you're asking questions, please sit in the middle so the camera can catch you. Maybe I can start then, because I have a question. So I'm at Fermilab, and we also have an accelerator. So I know I'm not that part of that group, but I know that our accelerator group is also super interested in. Also, could you say a few sentences about that project?
Right. So it's actually a very recent project we're starting in collaboration with Los Alamos. They have this kilometer-long, I think, particle accelerator called LANCE, and then they were using particle in the cell simulation for it. And currently the control of it is like very manual tuning. So each year they shut down the system for a few months, and when they restart for the experiment, it takes the engineers or physicists like several weeks to retune the system. So what we're currently doing is we're leveraging those simulator to generate a lot of data, given different initial conditions. And essentially we're developing a neural operator based surrogate model to predict those particle in the cell simulations. And we're trying to incorporate some physics into it so we can ensure the predictions are physically meaningful. That is our current progress. But later on, we also want to exploit this surrogate model, right, to train a better controller to reduce the amount of human labors in tuning the systems.
Thank you. I guess one tiny follow-up. Are these models, once you have pre-trained them, would they be small enough to fit on some FPGAs or somewhere so that the controls are actually automatic and close to the system?
That's a good question. I think so. The surrogate model may not be smart, right? But then that is the main goal of that is faster, right, than the particle in the cell simulation. And then later on, if we're training a controller, right, by assuming the surrogate model is a true system, I think that just accelerates this training loop, because otherwise you need to kind of try something new and then plug into this particle in the cell simulation, right, to see the result outcome and then to tune it. But now with this neural operator model, it's a faster prediction, right, of the experiment outcome given this new controller. So I think it kind of accelerate the design life cycle. But then if the controller is smart enough to embed in an FPGA, that's an interesting question. I don't know, but I think the previous scientist we collaborate with, he designed some rule-based controller that was coded into an FPGA. But we don't have any experience on kind of see whether a neural operator model, a neural network or neural operator model can fit into, those limited resources.
Amazing, thank you.
Thank you.
Yeah, maybe in the future, hopefully.
Yeah, maybe in the future. Thanks.
Thank you.
I will share the knowledge as we learn.
Any other questions? Yes, go ahead.
Oh, yeah. Hi. Thank you for the talk. Angelos Katsagalos, I'm here at Northwestern. I have two questions. The one is kind of generic. I saw a lot of the stability results. I know they're norm dependent, and in all your results, you use the L infinity norm. Is that the kind of what is preferred, let's say, in control problems to control the maximum deviation type of thing? Or is there any implication on that? I assume you couldn't show the stability results using, I don't know, the L2 or any LP norm, right? So anyway, that's the first question. If there is something to be said there, that the dependency on the norm, and in particular the L infinity you used. My second question is the acceleration you mentioned is you compare using a traditional, I guess, solver there, a classical one, versus the trained network, which is a feed-forward network. And I assume these are, I didn't see the description, there's small kind of networks, right? Fully connected networks with maybe, I don't know how many layers. So that's the 1000, for example, acceleration you mentioned, is comparing, it's hard to write a feed-forward pass versus using a classical solver to solve that K or whatever you're looking for.
Okay, yeah, thank you so much for your question. So for your first question, yes, so we use our infinity norm in our result. That is more relevant to this learning arrow we got is also in a flavor of our infinity sense, right? Because this is for all point you want to query your output function and, right, in the output function domain, right? So, and you can always maintain this approximation error of epsilon. So that's why more naturally we use this infinity type of guarantee, right? But if we want, if we really want, we can also kind of convert this epsilon to a L2 type of bond and then get some like guarantees over there. But that is kind of the motivation why we want to, why our guarantees are in the L infinity norm. And for the acceleration, right, so I think depends on the neural operator we use. For example, this for the first set of experiments, as I mentioned, there are many type of neural operator architecture design to date, right? And as long as they fit into this universal kind of representation from Andrew's paper, and they can hold this universal approximation guarantees, and they can work in our control applications. And the size of the neural operators, right, well, depends on your design. For example, some of this neural operator transformer model, like the foundation model, they can have billions of parameters. And for our first application, for approximating the OD solutions, we were using the FNO. So they have roughly millions of parameters there. And then for this PD application, for this hyperbolic system, actually we're using DeepNet and a pretty small network because that is just approximating integral equation solution. I think that one we kind of trained within a few hours. So it actually depends on the problem we're solving and kind of how challenging, and depends on the architecture you choose. You may end up having a different number of parameters.
No, I realize that, but since you mentioned 1000x, so for the second problem, you use the DeepNet, you're saying, for the first one, the FNO.
Yes.
So therefore, back in your last comment, how much you depend on data to do supervised learning depends obviously on the size of the networks.
Right.
And things like that. Okay. But back to the first one, it's not always the case. You can show kind of a stability result using any norm.
Yes, exactly.
It's norm dependent. So the fact that you show for L infinity does not mean that it holds for L2, right?
Yeah, exactly. Because those are the infinite dimensional space, so they're not equivalent. Yeah.
Okay. Thank you.
Yeah, thank you.
All right. Can I ask a question here? So you showed a lot of results in the control space about stability. I think
Right.
for the audience here, we're thinking about physics constraints, like
Uh-huh.
how to, we'll also kind of replace the PDE, but we want to
Right.
make sure the overall system would be physically feasible. Could
Mhm.
you comment a little bit on how your technique might be able to transfer over to that space?
Yeah, exactly. So I'm happy to talk about that. Actually, you can, when you train the model, right, rather than only using um, prediction error as a loss, you can incorporate some physics loss as your loss, right? You can use a physics informed network type of loss. And you can also design the neural operator architecture, right, to encode the physics properties. This is a part I skipped. This is one problem we designed for the motion planning case, and which we designed a neural operator we call the planning neural operator, physics informed PNO, planning neural operator. And this is kind of how we encode some of the physics that we think are important there. Through both a loss, soft penalty, a loss function, and also like architecture design. So our goal is to design neural operator that gives us a value function in the motion planning. Let's see, this is your starting position. This is your goal position. So you need to figure out a path from the starting to the goal. And the method there is if you can solve a value function for this problem, you can just follow the gradient direction, right? Because the goal position have the least value, and then you start from somewhere and you go there, right? So in this problem, yeah, where we do in this physics informed design is we kind of just hard encode all these obstacles because we don't care about the value function there, right? We hard encode the boundaries of the obstacles as a complex boundary condition for this system. And then we are masking out all the values inside the obstacles so that for our prediction of the value function, you can see it's all masked out in this right inside this obstacle area. And yeah, so that is how you can handle this very complex geometry. And also another thing we know is this value function should have some triangular inequality. That means if you query any arbitrary points and if you have a goal position, right? So yeah, this triangular inequality should always satisfied. So we also encode this triangular inequality. Maybe in your case, you have some conservation law, right? Or equivalently, you have some symmetry. So you can also hard encode those, right, into part of the design, right? So by design, your neural operator guarantee this conservation. So instead of predicting the magnetic field, maybe you're predicting some conserved quantity of it, right? So that you can always guarantee this hard constraint. And then furthermore, when we train this neural operator, we're not only using the prediction error, right, the supervised loss, we also encode the PDE as a physics informed loss because we know our prediction should satisfy this ACNOL PDE. So we actually just take the gradient of your prediction, right, with respect to x, and then try to enforce this PDE as part of a soft constraint. So those are some ways we explored in this motion planning application, how to incorporate physics as a soft loss function, like using a pin loss, or like as a hard constraint into the architecture design, if that makes sense.
Yeah, thank you.
Thank you.
Hi, I'm a graduate student. My
Hi.
name is Philip. I just had a quick question about the ease of convergence of neural operators,
Okay.
specifically with respect to the sampling.
Uh-huh.
So, like, if you were to sample your boundary conditions or initial conditions
Right.
more informatively, do you see that it converges faster, or versus just sampling on the grid, would it converge slower? Are there any things that you've been seeing, or are there any like theoretical things that can be said about how the network will converge? I know you talked about the universal approximation theorem, but finding those weights, is it easier if you have more informative sampling or not?
Oh, that's a great question. Actually, I think that's an open question. That is what I mean by functional encoding. Yeah. I don't see much work. I think there are a few recent work if you search on like sampling and neural operator, right? You may see like a few works, and but I don't think this has been rigorously studied or understood properly. Currently, I think what is used more often in both DeepNet, FNO, or other neural operators, they're mostly using uniform sampling of the function, but that has some obvious drawbacks. As you can see, if your function kind of is very flat, right, actually you can sample less, right? But if your function varies a lot in some region, ideally you want more samples, right, in those regions so you can capture the function. But I think for their current setting, they're assumed like the sensor location are fixed. So that's why you get those fixed point function evaluation. But what is the best way of representing the function, and how do you how do you design this smarter sampling algorithm of the functions? I think it requires more research on that. Yeah.
Okay, great. Thank you.
Yeah. We have tried something, and but we don't have some any positive results. And something we observed is we actually have tried something on kind of important sampling with respect to the function Lipschitz, because we thought it's intuitive. If the function change more fast, right, in some region, you want more samples, so that's why we designed that. But we can observe some benefits if in a low sample domain, if you can only sample, let's say 30 points of the function, right? Sometimes when you design this smart sampling approach, it can improve the neural operator approximation result. However, as you scale up these things, actually those smartly engineered sample approach by ourselves, by our group, does not tends to maintain the advantage. What we find is as we gather more samples of the function, actually those more general sampling scheme like uniform sampling or some other popular scheme actually tends to outperform those ones we designed based on the function Lipschitz, at least.
Okay, yeah, that's very interesting. Thanks.
Thank you.
But if you go non-uniformly, then you have to map to uniform. If you have to use the FNO, right, you have to use a discrete Fourier transform of non-uniformly sampled signals, which is kind of an issue by itself, right? So you might lose some accuracy there, I think.
Right. In FNO, they have this projection layer in the very beginning to handle that. That
right.
is this P. Yeah. So if you remember here, so they're not dealing with the original sample function, but they first have this projection layer, and this P is learned. So this is how they handle the different sampling regime or irregular samples.
Right.
Thank you.
Right. If there's no further question, let's thank our speaker one more time.
Yeah, thanks so much, everyone, for the question, and I really appreciate it. I'm sorry that I cannot be there in person, but feel free to to reach out, or if you have questions or just want to have more chat on these topics.
Thank you.
Great, thanks. And then do we have any announcement? I think there's a faculty lunch happening.
Yes.
Where?
Just
Where the food is. Yeah. Okay. All right. Next we have lunch.
Thank you.
Thanks, everyone. Thanks, everyone online as well.
there's
Thanks for
lunch
joining.
for there's food for everyone. We're just
Yes,
asking
yes.
the faculty to sit together.
Right.
Yes, there is.
Everyone eat.
Sorry, Yuanyuan, there's no food for you, but thank you so much.
No problem.
Thank you.
Yeah, thanks, Ermi. Thanks.
Thank you.
Thanks, everyone. Bye.
Bye.